We expect a lot from the hardware rushing past you on screen. We demand flawless 4K video streams, instant multiplayer gaming, and impenetrable banking security. And we expect all of it to happen at the exact same time. But the internet is essentially a chaotic web of cables. If engineers tried to force every piece of data running through those physical lines to follow a single set of rules, the entire system would collapse. Think about the different requirements. Rules built to heavily encrypt and verify banking transactions take time to execute. Apply those same heavy checks to a video game, and the action becomes unplayably laggy. Conversely, if you apply a video game's emphasis on pure speed to your email, you end up dropping important messages permanently. This is where protocols step in. They are invisible, highly specialized translators that instantly swap out depending on the specific task you are performing. The network holds together precisely because of this fragmented complexity. The entire internet functions on specialized engineering trade-offs. To even get on the network, your device needs an address. A protocol called DHCP works in the background to automatically assign you an IP address the second you connect, sparing you from taking a manual IT exam every time you join a Wi-Fi network. Once connected, you need a map. DNS acts as the internet's phonebook, translating human-readable names like google.com into numeric IP addresses. Now we follow that IP address into a larger maze. BGP takes over, calculating the best path to reach your destination. BGP is incredibly powerful and highly fragile. It implicitly trusts the route announcements it receives, meaning a single misconfigured routing instruction can accidentally send an entire country's internet traffic offline. DHCP, DNS, and BGP successfully get your data to the right door. They do absolutely nothing to dictate how that data behaves once it enters. That requires solving a completely different engineering problem. This animation illustrates TCP/IP, the reliable workhorse of the internet. Before sending anything, it performs a strict three-way handshake, checking in, confirming readiness, and acknowledging the connection, before guaranteeing the perfect sequentially ordered delivery of packets for web pages and emails. The flaw with TCP is that it is overly polite. If a single packet gets lost during a live video call or a multiplayer game, TCP stops the entire stream to go back and retrieve it, causing massive, noticeable lag. For real-time applications, engineers switch to UDP. UDP is fast and reckless. It strips away all handshakes and safety checks, blasting unnumbered data instantly. If some blocks vanish or arrive out of order, it simply doesn't care. The forward flow never stops. Recently, Google developed a hybrid solution called QUIC. It runs modern web traffic over UDP, capturing TCP's reliable delivery without sacrificing UDP's aggressive connection speed. Every skipped frame in an online game or brief loading pause on a website is an intentional engineering choice, prioritizing either perfect accuracy or relentless speed. Look at this room of early network users. During this high-trust era of computing, foundational protocols like FTP, plain HTTP, and basic SMTP were built entirely without security. They sent all data in easily readable plain text. Anyone sitting on the same network could intercept that plain text. Passwords, emails, and financial details traveled through the cables like open postcards. This vintage Netscape browser interface marks a crucial turning point. In 1995, Netscape created SSL, establishing the first cryptographic bodyguards alongside tools like SSH. These protocols scrambled data into unreadable code. Today, modern TLS handles this task. It verifies server identities, upgrading basic HTTP to HTTPS, so your browser knows you are talking to your actual bank and not an imposter intercepting the signal. Without this invisible, mandatory layer of cryptographic trust, the modern global digital economy would collapse entirely. Watch this stack lock into place. Clicking a single link triggers all of these agreements instantly. DHCP connects your device, DNS translates the name, BGP routes the path, TCP delivers the packets, and TLS secures the contents. The interface quirks we see every day, the padlock icon in the address bar, a brief loading screen, or a skipped frame in a live broadcast, are the visible artifacts of these invisible rules at work. The internet relies on physical hardware, but at its core, it is a fragile, brilliant consensus of millions of devices constantly agreeing on exactly how to communicate. The internet connects the entire world, but its greatest achievement lies in the silence of its operation. These millisecond negotiations happen flawlessly behind the scenes, allowing us to hit send, stream, and play without ever having to think about them.